Hello, we were discussing the concept of countability. In the last class, we have seen that if you have two countable sets A1 and A2, their union is also countable. And we have also seen that if you have finitely many countable sets like A1, A2, A3, etc. up to AN, then the union A1 union, A2 union, etc. union AN is also countable. Now we are going to ask, if you have infinitely many countable sets, and in fact countably many countable sets like A1, A2, A3, etc., then is the union A1 union, A2 union, etc. is also going to be countable? The answer is yes, and we are going to prove it in this session. This fact is known to us. That is, if A1, A2, etc. AN, there are finite number of sets, all are countable, then the union of these sets is also finite. This is known. Now, let us consider the set of all rationals once again to get our new question. So, set of all rationals we can write like this: 1 by 1, 2 by 1, 3 by 1. That means all rationals with 1 in the denominator, 4 by 1, etc. Now, we are going to write all rationals with 2 in the denominator in the following way: 1 by 2, 2 by 2, 3 by 2, 4 by 2, etc. Now after that again 3 in the denominator, 1 by 3, 2 by 3, 3 by 3, 4 by 3, etc. So this set, suppose that we call as A1, this set we call as A2, this set we call as A3. Therefore we have many sets like this, and therefore considering all these sets, we have all these sets are countable because we know that 1, 2, 3, 4 we are counting. 1, 2, 3, 4 we are again counting. So A1, A2, A3 are all countable. So AI is countable. AI countable for each I. For each I. This is clear. And Q equal to the set of all rationals equal to union I from 1 to infinity. AI is also countable. So motivated by this example, probably we may ask that if A1, A2, etc. are all countable sets, and suppose that there are infinitely many such sets, countably many such sets, then the union is also going to be countable or not? That is a question that we are going to ask now. So question is the following: suppose that we have A1, A2, etc. Suppose A1, A2 or AI are countable sets where I equal to 1, 2, etc. There are infinitely many. Then union I equal to 1 to infinity, AI is also countable, and the motivation is coming from this set of all rational numbers. As we have seen in the rational number case, there are possible duplications in these A1, A2, etc. in the sense that here we have 1 by 1 appearing in A1. So here 1 by 1 we have, and here 2 by 2 is the same as 1 by 1. Therefore, there are some possible duplications. To avoid these duplications, so that we can construct safely a 1, 1 onto function, we are just going to rewrite A1, A2, A3, etc. in the following way. So our rewriting is the following. So write B1 equal to A1 itself. After that write B2. We want to take all elements in A2, but if some elements in A1 is appearing in A2, we want to avoid them. So B2 is nothing but from A2 remove all elements in A1 possibly appearing in A2. So B1 and B2 are therefore disjoint. Now B3, suppose that we take it to be from A3, we are removing all the elements appearing in A2 union A1. So if some elements are there in A2 or A1 that's appearing in A3, we are removing them. Therefore, B1 intersection B2 is empty, B2 intersection B3 is empty, B1 intersection B3 is empty. All these are pairwise disjoint. So in general, BI equal to AI minus union AI minus 1 union etc. Union A1. So the way in which we constructed this BIs, bi intersection bj is equal to phi if I not equal to j. That is one property. So property number one of bi's are this: bi intersection bj is empty because whatever duplicate elements are appearing, we have all removed. We have removed them all, and the way in which we constructed bi guarantees that one of the bi, whatever bi we are taking, that is not going to have any intersection with some other bj. Next, property number two is bi are either finite or countable. So what is the reason for saying this? Because bi is actually a subset of, because bi is nothing but it's a subset of ai. ai is countable, and we have already seen, see, bi is obtained by removing a few elements possibly from ai, and therefore bi is a subset of ai. And subsets of countable sets, we have already seen that they are either countable or finite. Therefore bi are all finite or countable. And the last property, which is very important, is that union I equal to 1 to infinity bi is the same as union I from 1 to infinity ai. This is because b1 already contains a1. Now b2 contains a2 minus a1. Therefore whatever elements we have removed from a2, those elements are all in a1. Therefore b1 union b2 is nothing but a1 union a2. Now b1 union b2 union b3 is nothing but a1 union a2 union u3. Therefore union I 1 to infinity bi is nothing but it's equal to union a. Therefore these three properties are satisfied by the bi's. Therefore to show that union I from 1 to infinity ai is countable, it is enough to show that the newly constructed sets, it is enough to show that union I from 1 to infinity bi is countable. So our question is now reduced to showing that union I from 1 to infinity bi is countable, but bi has the extra property that pairwise bi's and bj's are pairwise disjoint. So that is the extra property that we have. Now we are going to rename or relabel elements in bi in the following way. So we know that b1 is either finite or countable. Therefore we can write b1 equal to b11, because this is countable or finite, b12, b13, etc. And this is possibly finite. This is because bi's are all countable or finite. We can label them like this. Now b2 equal to b21, b22, b23, etc. And in general, so we have bi equal to bi1, bi2, bi3, etc. So we have a labeling for b1, b2, b3, etc. Now, as in the case of the proof of the countability of rationals, we are going to just use the same technique in here. Write xn equal to bij from union I from 1 to infinity bi, where I plus j is equal to 1. So this is exactly the same procedure, the same technique that we used while trying to prove that the set of full rationals is countable. There, instead of xn, we named it as a. So what is x1? x1. So we want bij in such a way that I plus j, sorry, this is not I plus j is equal to 1, this is I plus j is equal to n. We want bij belonging to union I from 1 to infinity, union I from 1 to infinity bi, where I plus j is equal to 1, but ij are all natural numbers. Therefore no two natural numbers together adding we can get 1. Therefore the set is just empty. So x1 is empty. Now x2 is equal to, in the same way, I plus j is equal to 2. Therefore this is b11, just one element. x2 x3 equal to I plus j equal to 3. Therefore b12, b21, That's it. Now x4 we are writing one more set, b13, b22, b31. There are three elements. So in general, can we say that how many elements do exist in xi? So in xi or xn, xn equal to b1 n minus 1, b2 n minus 2, etc. b n minus 1, 1. So how many elements are there? So xn consists of bij with the property that I plus j is equal to n, and I plus j is equal to n in how many possible ways, where I and j are natural numbers. We have 1 plus n minus 1, 2 plus n minus 2, etc. n minus 1 plus 1. So there are n minus 1 ij's. So the number of elements in xn is equal to n minus 1. Therefore xn has n minus 1 elements for n equal to 1, 2, etc. So all these sets are finite sets. Now we are going to label xn's. And one more thing, one more important thing, that all these xn's are disjoint, because we have all these bi's are disjoint, and we are collecting them into some particular xn depending upon the sum of the indices. So xi's are all disjoint, finite, and union I from 1 to infinity xi equal to union I from 1 to infinity bi. Now we will label xi's so that labeling will be applicable for bi's also. The labeling is the following. So x1, this is empty. So x2 we are going to write. x2, what are the elements? x2 consists of elements b11. x3 consists of elements b12, b21. x4 consists of elements b13, b22, b31, etc. Now we label this one as the first one. b1 is first, b12 is second, b21 is third. See, we are labeling all elements, and x1 is empty, no elements. No elements are here, so we just keep it. x2 consists of b11, label it as the first element. x3 consists of b12 and b21. We may label either of them as the second element, and either of the other one as the third element. But instead of that, we are starting with the least number in the beginning. So b12, the first element in this set, so that is given the label 2. b21 is given the label 3. This is after that. Now we come to x4. The first element is 1, 3, 2, 2, 3, 1. So we are labeling 4, 5, 6, and we proceed like this. So observe that, as in the case of the set of all rationals, this labeling is well defined. 1, 1 and on. So as in the case of the rationals, we have verified that this is well defined, 1, 1 and on 2. Therefore union xi equal to union bi equal to union ai. All these unions are same, and this is countable. So we establish that countable union of countable sets is again countable. So to summarize, we have all these three results. 1, union of two countable sets is countable. 2, union of finitely many countable sets is countable. And the third one that we just now established, union of countably many countable sets is countable. So we establish all these three facts. So these are the main results regarding the union of taking union of countable sets. Of course, taking intersection of countable sets is again going to be countable, because we know that the intersection of countable sets is going to be less than each of the set in the intersection, and therefore since each are countable, subset is also going to be countable. So the intersection is not very interesting for us. Of course, that's also true. The intersection of two countable sets is countable. Intersection of finitely many countable sets is countable, and intersection of countably many countable sets is again countable. All these results trivially follow.